for us, there's really only one kind of function we know that has a maximum or minimum value, and that's a parabola or a quadratic function, right? We've seen parabolas either have a minimum if they open upwards or a maximum if they open downwards. So we're going to exploit that fact to find the maximum, minimum, or values of some situations that we're going to set up right now. So some of these take a little bit of writing. So bear with me. These are kind of real world problems. I feel like some of them are more real world than the other. So let's start off with kind of a classic example. A farmer has 120, is that the right number? Linear feet of fence to build, to build a rectangular corral for his animals or her animals. Their animals. To keep the horses and the cows separate, we also want a dividing fence. The farmer needs a dividing fence. Oh, by the way, this is all spelled out right in the note. So if you don't want to write it all down, you can look at the notes. So what dimensions of the fence will maximize the area enclosed? Okay. So typically there's a number of steps that I kind of go through whenever I'm doing an optimization problem. And kind of what I like to call, I wrote it as the first step on the notes, but I actually like to call it the zeroth step. Really. So step 0, draw a picture. If it makes sense to. Some setups, it really doesn't make sense to draw a picture. This one, it totally does. So I'm going to draw my rectangular corral. And then there's also a dividing fence in the middle. And I'm going to label what each side length is. I'm going to label this side length Y. I'm going to label this side length X. You are obviously welcome to make other choices, right? Any letters will do. The thing to keep in mind is that you want to use as few variables as possible, meaning I shouldn't call this X and this Z if they're really the same thing, right? The same length should get the same letters for their variables. So step 1, what are we trying to maximize? So we're trying to maximize the area. So I want to write an equation for the thing we're trying to maximize. So area is the area of a rectangle, is X times Y. And something important to be aware of is that the thing you're trying to maximize or minimize should never be equal to a number, right? We don't know what the maximum area is. It wouldn't make sense to say this is equal to anything numerical because we don't know what that is yet. The second thing we need after we find the thing we're trying to optimize is we need a constraint. Some sort of limiting factor. In this case, we are constrained by how much fence we have. We have 120 linear feet of fence. So what that means is that the amount of fence, which is described by X, X, Y, Y, and Y, all of those have to add up to no more than 120. So I'm going to say that X plus X plus Y plus Y plus Y is 120. Or more succinctly, 2X plus 3Y equals 120. Okay, so then after we find a constraint, we want to solve for one of the variables. Sometimes it's an obvious choice which one is better. Like if this had been just, I don't know, there really isn't either one feel more obvious. Here, you can kind of pick either one. I think in the notes, I picked solving for x. So I'm going to subtract 3y from both sides. And then divide both sides by 2. So that x is equal to 120 divided by 2 is 60. And 3 divided by 2 is 3 divided by 2. So we have minus 3 halves y. And then what we're going to do with that is we're going to plug that back into the thing we want to optimize. So step 4, plug in to the quantity we want to optimize. So in this case, I'm going to plug in x equal to 60 minus 3 halves y for x here. So I'm going to have that my area is now 60 minus 3 halves y times y. And notably, the area of this rectangle is now a function of just y. And I'm going to multiply it out to make it a little easier to see what's happening. So we've got area equal to, we distribute the y, we've got 60y minus 3 halves y squared. And I might rewrite this in a more standard way where the higher powers come first. So I might write this as area equals negative 3 halves y squared plus 60 of y. Great. So the area as a function of y is quadratic. And we know that a quadratic thing has a maximum or a minimum. In this case, it would open downwards because the leading coefficient is negative. So we know it has a maximum. So we have a maximum at the vertex. Now, a couple things to be careful about here. I'm not using the usual x, y variables kind of in the normal way, right? What I'm really actually thinking about, I'm going to draw this on the other side, so I'll come back to this for a second, is that if I was going to graph that equation, area equal to negative 3 halves y squared plus 60y, I would be thinking of my x-axis as actually being the variable y, and my y-axis as actually being the variable a. Right, because a is a function of y. And so this is going to look like some downwards opening parabola, and we're going to find the maximum at the vertex. So I'm going to write this in kind of a funky way. The coordinates of the vertex, the usual x coordinate, or the first coordinate, I should call it, is going to be the y value, and the second coordinate is going to be the a value. Right? If we use different letters than usual, we have to kind of think about that when we're doing our stuff. So I want to find the first coordinate, meaning I want to find the negative b over 2a. So I know it's going to be kind of weird to write this, but I'm going to say that my y coordinate, which is the input, that's going to be negative b over 2a. So that's going to give me negative 60 over 2 times negative 3 halves. That's going to be negative 60 over negative 3, which is 20. And typically at this point, I guess this would be the next step, right? This is step 5, finding the vertex. Typically at this point, you want to ask yourself what you're trying to find. Because sometimes the question is going to be, what's the maximum area? And if I was trying to find the maximum area, I would plug 20 back into the area equation, maybe even right there, and figure out what the area was. But that's not what they're asking for here. The question specifically said, what dimensions will maximize the area enclosed? So I want to find the dimensions, which I have labeled x and y. I found y, right? Y is equal to 20 feet. To find x, I'm going to use the equation that says x equals something with y in it. So the x value is going to be 60 minus 3 halves times 20. 3 halves times 20 is 30. 60 minus 30 is 30. So x is equal to 30 feet. And those are the dimensions that maximize the area enclosed. We could also, at this point, multiply x times y to get 600 feet squared, which is how much area is being enclosed. The question doesn't ask for that, but it is something we can still see. So if you do 20 times 30, you get 600. Or if you plug in 20 for y right here, you would also get, right, if this is 20 and this is 20, you're going to get 20 times, this is going to be 30, and 20 times 30 is also 600. So just make sure you're careful when you read the question that you know what you're looking for. You're always going to want to find the vertex of this parabola. It just depends on what you want to do with it, right? We found the input coordinate, right? So we found, right, this vertex here is 20, 600. But we were only asking for the y part, right? Because that was one of the dimensions, and then also the x part, which came from somewhere else. So just be cognizant of what you're being asked for. I'm trying to say it 5 more times in a different way. Yeah, that's it. So this is kind of the usual process for doing an optimization problem. You're going to find an equation for the thing you want to maximize or minimize. You're going to find a constraint if you need one. Where did the 600 come from? So this 600 is what the area is when you plug in 20. So, right, so here are the y values. Here's y equal to 20. Here's y equal to 40. And I know these because I'm familiar with this parabola, but we could also look. So if you look back here, right, area was a function of y. So if you say, right, in fact, you can even see that if y is 0, area is going to be 0. And if y is 40, well, if y is 40, we're going to use up all our fence, right? Because if y is 40, you got 40 plus 40 plus 40, which is 120. So if you use up all your fence for the y part, the x part is 0. So you got no area. So if y is 0 or y is 40, we get 0 area. And then in the middle, when y is 20, that's where the vertex is. And the area coordinate of the vertex, which is the second coordinate, which is the y coordinate, right? If it's x, y, I know, right? Variables can be kind of confusing, but the 600 is coming from plugging in y equal to 20. So I plug in y equal to 20. I could plug it in here, but it's kind of hard to do that math. I'd rather plug it in here and see that, oh, 3 halves times 20 is 30. 60 minus 30 is 30. And 30 times 20 is 600. So that's what's happening there. But what I was really trying to point out is that you don't always need to find this second coordinate of the vertex. Right? If they're asking you what the maximum value is, then you probably will. If they're asking you what the dimensions are that maximize the thing, probably not. But this is the process. We write an equation for the thing we want to optimize. We find a constraint if we have to. Then we find the vertex of the parabola. And then we kind of assess what we actually are trying to find. So let's look at this next question. The company has determined that its total revenue, I'm not going to write all the words here, so total revenue in dollars for producing a product can be modeled by R equal to negative x squared plus 450x plus 5,200. 5,200? No, 52,000, sorry. And I would mention here that you can say R equals, you could also incorporate the functional notation and say, right, R is a function of X. That would also be fine. Where X is the number of units produced. And sold. What production level will yield the maximum revenue? So this problem actually is much less kind of steps to figure out what's going on. So there is no step 0, right? I can't draw a picture that really makes, I mean, I could draw a picture of the graph of this, I guess, but right, there's no like picture of what is being modeled by the situation. There's no fence, there's no circle, right? But I do know that, so step 1, I want to maximize this function. R of x equal to negative x squared plus 450x plus 52,000. Step 2, constraint. There is no constraint, right? We've already been given, so I should go back to the other side for just a second. Here we were trying to maximize something that had 2 different variables, and that's not something we're capable of doing, right? To maximize a function, we really have to have it be a function of 1 variable. And so we need the constraint so that we can write one of the variables in terms of the other, if the thing you're trying to maximize is in terms of 2 variables or more. But in this case, since the thing we're trying to maximize is already expressed as a function of just 1 variable, there's no constraint to find or be bothered with. So we're just going to find the vertex, right? We don't need to solve for x in terms of y. We don't need to plug back into the equation. We're just going to jump straight to finding the vertex. So we know how to find the vertex. The x coordinate of the vertex is negative b over 2a, which is going to be negative 450 over 2 times negative 1. I guess I should ask before we figure this out. Is this quadratic going to have a maximum or a minimum?
Maximum, right?
Maximum.
It's going to be a maximum. We know it's a maximum because that negative x squared means it's opening which way?
Down.
Down, which means the vertex is the highest point. So yeah, so if you've got a negative out in front, you have a maximum. Also, I shouldn't be asking you to find the maximum if it really has a minimum, right? That would be not nice. It's all right, no problem, cool. So yes, I won't be asking you for the wrong thing, but it's good to like think about, do I actually have a maximum or minimum here, right? And that actually becomes kind of a bigger point of contention when you get to doing this in calculus. But not here. Here, if the parabola we know opens upwards, you got a minimum, opens downwards, you got a maximum. So this is going to be, let's see, 450 divided by 2 is 225. Okay, so let me ask you, did we answer the question? I think we did, right? They said what production level, meaning how many units do we have to produce to maximize the revenue, to yield the maximum revenue. So yeah, x equals 225 units will maximize revenue. They did not ask us to find what the maximum revenue is. We could find it if we wanted to, right? The maximum revenue would be the function coordinate or the y coordinate of the vertex, right? So if you wanted to, you could say that I'm going to call it VR, right? Because the function's r of x, right? So my vertex in this problem, I'm calling Vx comma VR. And to find the r coordinate, I'm just going to plug in 225. So I'm going to get negative 225 squared plus 450 times 225 plus 52,000. I don't really want to do this work. I just want to point out that's how you find it. I will tell you that the one thing I do want to ask you guys is negative 225 squared. Is it positive or is it negative?
Positive.
Ooh.
Is it negative?
Ooh.
Because there's no parentheses.
Right, there's no parentheses. So since there's no parentheses, that square has to happen before the negative. So it is negative. So it ends up being negative something, I think negative 50,625 plus 100 and something thousand, right? This ends up being 102,625. But yeah, be careful. This part right here is negative. So if they asked you what the maximum revenue was, it would be $102,625. Ooh, sorry. Chair, go away. Okay. So I'm going to re-emphasize here. When you're trying to maximize or minimize a function, you're just looking for the vertex. If they're asking for what values make it a maximum or minimum, you're usually looking for the input values. If they're asking for what the maximum or minimum value is, you're usually looking for the second coordinate, the output value. So let's look at this next question. And I'm going to maybe word it slightly differently. And this does come from it should be noted, this question comes directly from a Math 16A textbook, but can totally be done without using calculus. So find the dimensions of the largest rectangle that can be. So when I say the largest rectangle, I mean the rectangle with the most area. So typically if I say something that's the largest two-dimensional shape, I mean it has the most area possible. If I say the largest three-dimensional shape, I mean it has the largest volume possible. But like if I said the largest rectangle, I wouldn't mean like the rectangle with the biggest perimeter, right? That would be a silly way of saying the largest rectangle. So largest rectangle by area. In the first quadrant, that can be inscribed under the line y equals 18 minus 6x. And here it definitely makes sense to draw a picture. Here's my step 0, drawing a picture. So it's got to be in the first quadrant, which is right the upper right quadrant. And it's got to be under the line y equals 18 minus 6x. Y equals 18 minus 6x has a y-intercept of 18, right? If I set x equal to 0, y is 18, and it has an x-intercept of 3. If I set y equal to 0 and solve for x, x will end up being 3, because we get 6x equals to 18 and x will equal to 3. So it's going to look like this. That point there is 0, 18. That point there is 3, 0. And the rectangle, so it could look like this, right? That's inscribed in the triangle. Right? It's under the triangle. It's not crossing over. It can't look like this, right? That would be too big. That's no longer inscribed. But this is a poor choice because I can clearly make a bigger rectangle by making this right corner touch the hypotenuse of this triangle. So that's what I'm going to do. So here is a representative rectangle. It is inscribed. It is using up maybe as much space as it can. All right. And so just like before, I'm going to label the sides of the rectangle. I'm going to label this. I'm going to do it slightly differently than what I did in the notes, just because it's good to see how things might be different. I'm going to call this the base and this the height. And I'm trying to maximize the area of the rectangle. So I'm going to try to maximize area, which is going to be base times height. And just like
Professor,
before, we were
maximizing.
Where did I get the 3? Sure. So I got the 3 by finding the x-intercept. So I set y equal to 0. And then if I solve for x, I get negative 18 equal to negative 6x, and then divide both sides by negative 6 to get x equal to positive 3. And I know someone else just said they had a question. Was that the question you had?
Oh yeah, I just had seen the notification pop up. I didn't know if you've seen it.
Yeah, thanks. No, but thank you for chiming in. I appreciate it. So we want to maximize this. There's 2 variables there. That's a problem. We need it to be one variable. So we need a constraint. So the constraint for this problem is the fact that the rectangle has to be inscribed under the line. Specifically, I'm thinking about the fact that this point here, this corner, is actually on the line. And I know the coordinates of that corner. I know that I went over B and I went up H. So this has coordinates B comma H. But I also know that the BH has to be on the line y equals 18 minus 6x. So my constraint is actually that the y coordinate here equals 18 minus 6 times the x coordinate here. So for example, if the base was 1, the height has to be on this line. So if the base is 1, the height would have to be 12. Because again, the rectangle corner is touching that line. Well, great. I've already even isolated one of the variables. So in this particular example, it should be relatively straightforward to see that we should definitely choose H to be the thing we solve for because it's already solved for. So now I'm going to plug that into the equation up here. So I'm going to say that area is equal to B times H, but H is 18 minus 6B. And I'm going to multiply it out so that I can see that it looks like a quadratic. This is going to be area equals 18B minus 6B squared, or if we prefer, area equals negative 6B squared plus 18B. Now we can find the vertex. I feel like maybe my numbering isn't always perfectly great. I guess that part 4 was whatever. Sorry about the numbering. Sometimes it's a little off. So to find the vertex, the input, which is the B thing, that's going to be negative B over 2A. I know this B and that B are not the same, right? So I'm going to call this, so let's see, negative 18 over 2 times negative 6, which is going to be negative 18 over negative 12. And that reduces to positive 3/2. So the base should be 3/2. And let's see, we're asked to find the dimensions. So if the base is equal to 3/2, then the height is going to be, let's see, I'm going to plug in, well, I've got an equation for height right here. So I'm going to plug in 3/2 for the base and get 18 minus 6 times 3/2. 6 times 3/2 is 9, right? You can cancel a 2 here, and a 2 here, and 3 times 3 is 9. And 18 minus 9 is 9. So the base is 3/2 and the height is 9. And if we were asked to find the maximum area, so I know this is not part of the question, but the maximum area would be 3/2 times 9, which would be 27/2. And I really want to stress to you guys, I guess on the other side, yeah, here. We didn't graph it, but if we had graphed the parabola, here's what it would look like. So again, my input is B for base, my output is A for area. And it looks something like, let's see, I can see that my intercepts are 0 and 3, right? If B is 0, the area is 0. If B is 3, the area is 0. It looks like that. I mean, right, that's it. And then my vertex here is B equal to 3/2 comma, a equal to 27 halves. But it doesn't tell us anything about what the height of the rectangle is. It tells us what the base of the rectangle is, what the area of the rectangle is, but to find the height, we had to use this constraint equation. You go back and say like, oh, if I know the base, I can find the height. Right. Really, only one more? But sometimes these often take longer. I can always make up extra questions, or I guess we could, it might be wise to try and catch up a little. Before I get ahead of myself, let's actually just do the next problem maybe. How about that, James? It's a good idea. Okay. So oh yeah, we'll probably do the next one because we'll probably start the next one because the next one is more optimization. So it seems very on point to continue with the same sort of stuff. So the next question is, which point on the line y equal to 3x plus 1 is closest to the point, closest to the point 2 comma 1? Yeah, 2 comma 0. So I will point out that this question doesn't specifically say to maximize or minimize anything. But once we start drawing stuff, it might become kind of clear. So let's draw y equal to 3x plus 1. It's a straight line. It's got a y-intercept of 1. If I set x equal to 0, I get y equal to 1. It's got an x-intercept of negative 1/3. Right? If I set y equal to 0, then 0 equals 3x plus 1. Negative 3x equals 1. X equals negative 1/3. So it's about, there maybe, sure. I don't have to be super precise with my picture. I'm just trying to be precise because it's good to be precise. So there's my line for lack of a. And now I want to find the point on this line that is closest to the point 2 comma 0. And I don't know where it is exactly. I'm just going to kind of make a guess. You don't need to know where it is exactly. I'm going to say it's about right here. I'm going to say it's probably more like right here, whatever. So I'm going to say, well, if this point's the closest, then the distance between these 2 points has to be small, minimize. So what this question actually says is minimize the distance between the point that we don't know on the line, which we're going to just call xy, and the point that we do know, 2, 0. So minimize the distance between this point here, which I'm calling xy. You can call it anything you want. And this point here, 2, 0. Okay, well, we know how to find the distance between two things. We saw the distance equation last class. So we're going to say that, so you can subtract either way, right? You can say that the distance equation is the square root of 2 minus x quantity squared plus 0 minus y quantity squared. But usually if you have variables, it's nicer to do the variable first, meaning I'm going to do it as x minus 2 quantity squared plus y minus 0 quantity squared. Now, I know what you might be thinking. Well, I think I know what you might be thinking. Well, actually, before we get there, let's do one thing. So that's our distance. That's the thing we want to minimize. And we need a constraint because again, the thing we want to minimize has 2 different variables in it. Well, the constraint is that this point is on this line. And if we're on that line, we know that y has to equal 3x plus 1. So we can replace y with 3x plus 1. So our constraint is that y equals 3x plus 1. And then our new equation is going to be that the distance between these 2 points is the square root of x minus 2 squared plus y minus 0 is just y, but y is just 3x plus 1. Now, I imagine you might be thinking, James, that's not a parabola. It's not a quadratic. And you're right. It's not a quadratic. So here is something that's true. And I'm going to write this on the next side. Actually, I'll give you guys a minute while I erase the other side. Ow! Quarter of stub toes. That's what it's going to be. It's all right. My toes are okay. Did someone say something? No, I'm just hearing my wife. Sorry. So here's something that's kind of neat that's true. If you're trying to make the distance as big as possible, it is equivalent to making the square of the distance as big as possible, or as small, because we're actually trying to minimize here. So if we're trying to minimize the distance, we can minimize the square of the distance and still get the same result. So I'm going to write that down over here, because it is something that, and we use this fact all the time in calculus, because it's way easier to deal with the thing that doesn't have the square root. So if we want to minimize or maximize the distance d, or I should say, the way I'll say it is this way: the value of x that minimizes distance also minimizes distance squared. So, and this kind of makes sense, right? If you're trying to make the distance as small as possible, you will also make the square of that number as small as possible, because it's always positive, right? If you had negative values, it would kind of be an issue. But right, if you're thinking about making some, right, if I was going to graph distance and distance squared, right, it's going to look like this. If I'm making the distance as small as possible, I'm also making the distance squared as small as possible. If I'm going this way on the graph, both things are getting smaller at the same time. So don't sweat too much. Don't worry about this too much. Just know that it is true. If you want to make the distance minimized, you can instead make the distance squared minimized. So that means we can minimize the distance squared. Well, that's nice, because the distance squared is just this same thing, except without the square root symbol on it. That's great. So that's going to be, I know I just looked at it. That's on my notes here. X minus 2 squared plus 3x plus 1. Yeah, plus 1. And now that we can multiply out and see that it is a quadratic. So that's going to be x squared minus 4x plus 4 plus, this one's going to multiply out as 9x squared plus 6x plus 1. In case you're not aware, just so everyone's okay, I'm just using the fact that when you have a plus b squared, it's a squared plus 2ab plus b squared. That's how I'm getting both of these here so quickly. Okay, so now if we put these together, the distance squared is x squared plus 9x squared is 10x squared. Negative 4x plus 6x is 2x. And 4 plus 1 is 5. And we can find the vertex of this parabola. So the x coordinate of the vertex is negative b over 2 times a, which is going to be negative 1/10. All right. So now we have to go back and ask ourselves, how do we answer the question? They said, what point on the line y equals 3x plus 1 is closest? So we found the x value of that coordinate. It's actually negative 1/10, which is like right here. And the y coordinate we can find by plugging in x into the equation of the line. So the x coordinate is negative 1/10. The y coordinate, I'm going to plug that into y equal to 3x plus 1. I'm going to get y equal to 3 times negative 1/10 plus 1, which is going to be negative 3/10 plus 10/10, which is 7/10. Okay. Yeah, so that's the point. So the point is negative 1/10, 7/10. If we had found the second coordinate of the vertex, that would have told us what the distance between, or it should tell us what the square of the distance between the 2 points was. So if you plug negative 1/10 back into this, you would get some number like, I don't know, some number close to 5, probably like 5 minus 1/10. And that would tell you, and then the square root of that would be the distance between these 2 points. But again, they didn't ask us what the minimum distance was, so we didn't find that thing. All right. I'm going to go ahead and do the next problem in module D. Sure, yeah, that seems reasonable. Back to ranching. So I'm not going to, so homework, so the schedule of homework is still just going to be that B and C are due on Monday, but we'll start playing a little bit of catch up and do at least the first problem from class D, which is still just more optimization. So here's the setup. Again, a rancher wants to build an enclosure for his animals. So I'm not going to write all the words this time. I'm just going to say the things and write down what's important. So we want to build an enclosure for his animals, and we want it to be rectangular. So rectangular enclosure. And here's what we have. We have that the fencing material for 3 of the sides costs $2 per foot. So 3 sides cost $2 per linear foot. We'll just say per foot. And the material for the 4th side costs a little more. It costs, oh, sorry, a little less. It costs $1 per foot. If the rancher can only afford to spend $500, so the budget's $500. I was kind of hoping this would be about fine. I was going to try and make this a little different, but that's fine. What dimensions will maximize the area? I was thinking we might say if we only have so much fence, what dimensions will minimize the cost? But it's not the case. And I guess that doesn't really make sense, but okay. Maybe we'll do that next time. So let's draw a picture. Here's our rectangular enclosure. It doesn't really matter which way you label things. Like I'm going to call this side X. Oh, no, that's fine. Yeah, this side X, this side Y, and this side Y. That might not be have been what I actually did in the notes, but that's okay. And then I want to write, well, I want to maximize the area. So I want to maximize area, which is still X times Y. And then my constraint now is my budget. So the way I'm going to write this equation with the constraint is that I need to know what the cost is. So which side do we want to say costs $1 per foot? It actually doesn't matter which one you pick as long as you just pick one. So let's say, yeah, let's say this side. And my picture is kind of also drawn the way where if you were trying to minimize the cost, you would want the longer side to be the one that costs less, but it doesn't really matter. You can pick X or Y. If you pick X and someone else picks Y, your answers will be reversed, meaning you'll have X being the longer thing and someone else will have Y being the longer thing, but it's okay, either way you do it. So the constraint then is going to be that $2 times this side plus $2 times this side plus $2 times this side plus $1 times this side is going to equal 500. So we're going to have 2y plus 2y plus 2x plus 1x equals 500. right? Because if like y is 10 feet, then this side will cost $2 per foot times 10 feet, which is $20, and so on. So I've got 4y plus 3x equals 500. And I'm going to solve for, let's solve for y, because dividing 500 by 4 is nicer than dividing by 500 by 3. So 4y is going to equal 500 minus 3x. Y is going to equal 500 divided by 4 is 125. And 3 divided by 4 is 3/4. So now we're going to plug that in to the area equation. So area is going to equal x times 125 minus 3/4 x. We're going to distribute it. So I'm going to write it the normal way. So I'm going to write it as x times negative 3/4 x will give me a negative 3/4 x squared. And then x times 125 will give me 125x. And to find the x coordinate of the vertex, that's going to be negative b over 2a. So negative 125 over 2 times negative 3/4. That's, let's just cancel the negative sign. So it's 125 over 3 halves. If I flip and multiply, it's 125 times 2/3, which is 250 thirds. So the x coordinate is 250 thirds, which I would leave as is. You could also, I guess, say it's 83 1/3, but I really don't like mixed fractions. We don't typically use them if we can avoid it. And we can always avoid it. And then to find the y coordinate, we're going to go back to this equation here and plug in what we found for x. So y is going to equal 125 minus 3/4 times 250 thirds. The 3's cancel. 250 over 4 is 125 over 2. So I've got 125 minus 125 over 2. And here's a nice thing I've noticed about like this specific kind of subtraction. If you have a number minus half of that number, you end up with half of that number. So 125 minus half of 125 is equal to half of 125. So this is going to equal 125 over 2. So the y value is 125 over 2. Or 62.5 if you prefer. Okay, so that is it.